Good afternoon. After seeing lots of geophysical data about the Lithosphere-Asthenosphere boundary, lots of modeling at the beginning between yesterday and today, I will try to show you a little bit of rocks that come from the Lithosphere-Asthenosphere boundary. So there are not many. You see that there are restrictions on which kind of rock we can sample. But the advantage of looking at rocks is that you can have a better idea of the complexity of the processes in the interaction between physical and chemical processes that take place in the Lithosphere-Asthenosphere boundary. So the data I will be showing you is work that we have been doing together in the group in Montpellier. And I will be showing mainly data from 3 PhD theses, Kate Higgy, Roberta Grusta, that is in the audience, and Veronique Leroux, and some of the ideas also come from work of Vincent Sustelli, even if I'm not showing directly his data. So just to remember what I have seen in the last 2 days, we have very nice geophysical observations that show that you have a topography in the Lithosphere-Asthenosphere boundary, that you have a sharp velocity decrease at the base of the lithosphere in many places of the world. And this kind of data has been interpreted either as the presence of small melt fractions in the asthenosphere, or you have to take into account more complex models where you have mental hydration that varies with depth and attenuation to explain this kind of sharp velocity contrast. So the presence of melt, the main problem is that it's easy to melt when you're shallow in the mantle. When the lithosphere-asthenosphere gets deeper, melting gets much harder. So we also have this kind of the work from Kawakatsu and his group that shows that if you get the melt aligned, you can explain the observations with much smaller melt fractions, so it helps a little bit. And when you get the melts aligned, also explain better the seismic anisotropy data. And to complete the kind of data set, the geophysical observations we also have electrical conductivity data, and here I found a figure that had not been presented yet, where you have beneath the trench here in Central America, you have this kind of, so this is the plate, the subducting, you have this kind of high conductivity region, and we also have a strong anisotropy in the conductivity. So the conductivity parallel to the trench is 2 times the conductivity normal to the trench. For explaining this data, water alone cannot explain it. You get a better explanation of the observations if you add water and melt. And if you want to explain the anisotropy, you also need the melt to be organized, to be aligned. This kind of observation also comes from some active plate boundaries, as we have seen in this morning, where you can explain better the seismic anisotropy observed in the East African Rift, both from SKS splitting, here also surface wave anisotropy. If you have both a preferred orientation of the olivine crystals in the mantle that is associated to the mantle, the flow of the solid part of the mantle, and some alignment of melt lenses or dike. This kind of data does not really give you a very strong constraint on the spatial scale of this alignment. It just says that it's smaller than the seismic wavelength you are using for doing the observations, but it can be kilometer, meter, or even micrometers. So we have to get a better look on how the melt aligns. If you look at experiments on systems where you have olivine and basalt, what you have is that when you are deformed the systems in presence of melt, you get the melt that is the black part here that tends to align at low angle to the shear plane. The shear plane is horizontal. So these alignments is just melt at the grain boundaries, but you have aligned wet grain boundaries. If you deform, you can also have segregation of the melt in melt-rich bands, the dark parts here. So it depends on the scale of the system, the compaction scale, length scale of the system. You can also either have a distributed melt that's aligned, or segregation of melt in bands. Here also the bands are at the low angle to the shear plane. And we also have another observation is that you change the way olivine deforms. Here you have the result of the olivine deformation that are the crystal preferred orientations that form. In a dry system, we have a strong orientation of the 100 axis that is parallel to the shear direction. In this kind of system, you have girdles of A and C axis in the shear plane, so it don't have this strong preferred orientation of the A axis parallel to the shear. In this kind of system, you have a switch of the direction that orients in the shear direction, and you have the c-axis that is oriented parallel to the shear direction. So these are kind of observations you get from the experiments. Do you see this kind of feedbacks in nature? So what I'll be showing you is some structural and microstructural data on mantle peridotite outcrops. So pieces of the mantle that have been brought to the surface mainly by tectonic processes. The first one will be dealing with a very shallow mantle. We'll be looking at an outcrop in the omanophyolite, which is interpreted as a region that is just close to an active mantle upwelling, where you get the mantle rocks that are still contain quite a lot of melt that is sheared sideways by the differential motion between the plate and the asthenosphere. So what we have been looking at, so we are very shallow, less than 10 kilometers depth, and we are looking at a series of samples along this continuous outcrop. So what you see when you look at this outcrop is that you have a layering, a compositional layering, that is marked by the variation in the olivine, plagioclase, and clinopyroxene content. The olivine-rich rocks that are yellowish ones here are the ones that are the mantle. The white layers here, they are rich in plagioclase and also have quite a lot of clinopyroxene. These rocks are formed by reaction between the melts and the mantle. So this is not frozen melt, but the fact that you have more basaltic components here means that you had more melt at one time in these layers. We also see that you have a very strong deformation structure. Here you see the flow direction, the lineation that marks the flow direction. And you see that this fossil melt-rich lenses are finite. They are like kind of elongated pancakes. If you look at the smaller scale, you see that we have the limits between these layers are diffuse, so they are not dikes, they are not fractures. And you have continuous variation in compositions from dunite, so full olivine, to levels that really have a gabbroic composition, more or less. You can go into still more detail and look like how the crystals are oriented in these rocks. So for that, you use the diffraction of electrons and analyze the diffraction patterns to get the crystal orientations. This is what you get in a dunite. So all the red here is olivine. The yellow is plagioclase. The green is clinopyroxene. You see that you have mainly an olivine rock, rich rock with some plagioclase. And here you have a layer that is very rich in plagioclase and clinopyroxene, but you still have some relict olivine. When you look at the crystal preferred orientations and layers of this composition, you still get a strong orientation of the A-axis parallel to the lineation, that is what marks the shear direction. A girdle distribution of the B-axis normal to the shear plane. When you get to the gabrous, you change the dispersion. You get the B-axis that is very strongly concentrated normal to the shear plane, and the dispersion of the A and the C-axis in the shear plane. And this kind of change in olivine crystal preferred orientation occurs and repeats itself over the whole section at the scale that you change the composition of the layers. So within a few centimeters, you can change completely the olivine deformation pattern. So it cannot be a change in the physical properties. You cannot change temperature or stresses at this very low scale. So the best explanation is that you have a varying melt amount fractions between the two layers during the deformation. So it's a quite good argument for melt segregation in layers parallel to the shear plane. And the change in crystal preferred orientation you see is exactly these two crystal preferred orientations you see here, the ones that are typical for dry systems in the experiments, and the ones that are typical for aligned melt in a deforming system in presence of melt. We don't see this one here. So if I resume, what we see in Oman, that you have shearing that results in alignment of melt-rich layers parallel to the shear plane, and that the presence of melt during deformation changes the way olivine deforms with a dispersion of the A-axis in defoliation. So we can ask ourselves if this kind of process can take place also in a normal mantle, where we have lower melt fractions and maybe lower shear strains also. So this is data from Lanzhou. So we are in the Alps here. It's a peridotite massif in the Alps. And we are looking at something that took place deeper. It's also a lithosphere-asthenosphere boundary. You have melt present in the system, but it's a little bit deeper. We still have the same kind of compositional layer you see in Oman, with plagioclase that are still marking where you have melt concentrations in the past, and the yellowish layers that mark where you have more olivine, so less products of reaction between the melts and the mantle. You see that you have at large scale a quite clear layering that's parallel to the deformation features, to the foliation, and you have delineation in these planes here. When you look at closer to it, you see that it's less organized in Oman. You have kind of an anastomosed structure of the melt-rich layers here, the plagioclase-rich layers. When you look at the crystal preferred orientations, and you have transitions, I forgot to say, from something that is where the melt is quite homogeneous distribution, you still have an orientation, preferred orientation of these plagioclase-rich pockets, to some places where we start to have a real segregation of plagioclase-rich and olivine-rich layers. When you look at the crystal preferred orientations, we have both patterns you saw in Oman, the ones with the girdle distribution of the A-axis and strong B-axis distribution, and some that still have a very strong B-axis distribution, but where you get the A-axis that is more strongly aligned parallel to delineation. And this kind of also change repeats itself over the whole system. And when you have this kind of more distributed area here, you alternate between the two patterns, and you cannot really distinguish between them just by looking at the field. One point that could be interesting for the seismologists I want to make here is that this kind of dispersion of A-axis within the flow plane, if the flow plane is horizontal in the asthenosphere, this kind of olivine preferred orientation can produce a higher radial to azimuth anisotropy as seen by surface waves, even if you don't have any melt present in the system anymore. Since I changed the way I deform the olivine, I can froze a different olivine crystal preferred orientation and change the pattern. This one produces a very strong azimuth anisotropy. Here, the azimuth anisotropy is weaker because the A-axis is dispersed in the foliation plane. What you can see also in Lanzo is you have chemical evidence for melt segregation in these plagioclase-rich layers. This chemical evidence is the change in olivine composition. So here, the dark symbols are magnesium-rich olivines, the light symbols are iron-rich olivines, and you see that you have more iron-rich olivines when you have plagioclase. For changing the olivine composition, you have to interact with lots of melt. It means that these layers here have seen more melt than the ones that are olivine-rich. So we also have here chemical evidence for variation in the melt content at the scale of the layering, align melt parallel to the shear plane, and this probably can give some of the anisotropy of seismic properties you see in the seismological observations, and it also will probably affect the mechanical properties. You can expect to have a lower shear viscosity parallel to these layers where you are concentrating melt, so I'm decreasing the viscosity than normal to it. One of the big problems, big discrepancies between these natural observations and experiments is that in the natural systems, I always have the melt line parallel to the shear plane, while in the experiments, there is always an angle of around 30 degrees. So this is very new data. I think it's impressive in geology. For some experiments where they have reactive systems during the formation, and what they see is that they have two orientations that form. So they have a system where they have olivine and a silica-rich melt. So a melt that will react with olivine to crystallize pyroxene. And when they freeze the experiments, they will have two products to look at. They can look at frozen melt. And this frozen melt will be rich in potassium, so they can map it by EDS. And they will also have the pyroxenes that crystallized by reaction. They will be richer in silica, so they can trace the orientation of both the products of melt rock reaction and the frozen melt in the system. And they have different orientations. The orthopyroxenes are merely oriented parallel to the shear plane, while the frozen melt pockets that are marked by the red arrows here, they have the same 30 degrees that you see in the previous basalt olivine experiments. So maybe you have different orientations when you have the melt present in the system and the products that you produce in the melt rock reaction. This is what we see in the natural systems. We never see this kind of stuff in the natural system. And so they produced an explanation why to get different orientations by saying that we start by orienting the melt in the extensional phases of the crystals. And in the compressional phases, you have concentration of dislocations and probably early recrystallization. And by grain size reduction, you just drain the melt into the systems and enhance the reaction rates. So we start by forming the pyroxenes oriented like this, and then by solid state deformation, you parallelize them to the flow direction. So this kind of data can be an explanation to explain the discrepancy between the experiments and observations, yet I'm not fully convinced that it works every time, and this comes from what we see in crustal systems, in migmatites, where you have the frozen melts in the system. There are shear zones in the lower to middle crust, so these are a few examples from Northeast Brazil, where you have partial melting during the deformation in the crust, and here these melts are not very mobile, so they are most frozen, in situ frozen melts, with very strong shearing, and most of these melt-rich layers, the light ones, the granitic ones, they are parallel to the shear plane here. So there's still maybe something that we don't fully understand between this kind of angle between the melt and the shear plane. If I try to go deeper, we can look at larger scale, and when you go deeper, we have something that's quite interesting, and that may explain a little bit how we can form new plate boundaries, at least extensional plate boundaries, is that you can see a moving lithosphere-asthenosphere boundary by interaction between chemical and mechanical process. So I will be showing you data from Lurz. So it's a peridotite massif in the Pyrenees. And what we see in Lurz is that you had a previous mantle lithosphere that was deformed, that has a refractory composition, so it was mainly Habsburgite. And then you had melt percolation through it. The melt reacted with the Habsburgites. It crystallized pyroxenes. We are deeper in the mantle, so we are not stable. Plagioclase is not stable anymore. So these pyroxenes will just transform the Habsburgites into lyerzolites, so you get more fertile another time. And you get a new deformation that follows this, that cross-cut the old Habsburgite foliation. And one of the main points to giving the timing between the two processes is that in the field we can map the foliation in the Habsburgites, and even if the bodies are separate, you have the same orientation all over the bodies. And you can also see that the lyerzolites cross-cut this foliation. So this is one of the examples in the field. You can see here the deformation features in the Habsburgites. You have the foliation that's marked by the grain elongation. Then you get these pyroxenite layers here that we have interpreted as melt accumulation horizons. They are oblique to the foliation, they cross-cut it. And then you have the lyerzolites that are almost undeformed. So we can only get the process by starting with the Habsburgites and producing the lyerzolites at the expense of these Habsburgites. When you look at the crystal-preferred orientations, you also have an evolution. The Habsburgites have very strong crystal-preferred orientations that are coherent with the fact that you see a very strong foliation in these rocks. Then you get to the contacts between the Habsburgite and the lyerzolite, and you see that you weaken this preferred orientation, but you still have the same pattern, just weaker. And you go farther away, a few meters away from the contact, you have a change in the orientation of the B-axis. This means the new deformation that is starting and rotating the initial crystal-preferred orientations. So what we see here is that you have a deformation that is following the reaction percolation front. So you get the melts that are propagating, and as they propagate, they weaken the lithosphere, and a new deformation can take place. If you look at the lyerzolites far from these contacts, so far from the percolating front where you have lots of melt in, they are very strongly deformed, while the ones here are very weakly deformed. These ones are very strongly deformed with very strong foliation. So these are the close to the contacts. These are the ones far from the contacts. You can have quite a lot of grain size reduction here too. We also have layering. So it looks like you have the same kind of melt segregation you have seen in Oman and Lanzo. And you can see that the idea you have higher strains here because you had higher melt contents in this area here that allowed for the full transformation of the Habsburgite into lyerzolites. When you look at the crystal-preferred orientations, you see the weakening I have shown in the first pattern. So this is the distance from the contact here in a Habsburgite body, here in a lyerzolite body. And this is intensity of the crystal-preferred orientation. So you get crystal-preferred orientations get weak. Then, and the patterns also change here. You see that you have more of this kind of girdle patterns we have also seen in Lurz and Lanzo and Oman. And when you get very far, you have much weaker preferred orientations that may suggest that in this rocks where you have more melts present during deformation, maybe you had other processes like diffusional process or grain boundary sliding that are also contributing to the deformation. But the fact that you keep crystal preferred dentations means that dislocation creep is still important and you don't have huge amounts of melt in the system here. If I try to summarize the observations we see in lerts, and they are also valid for Ronda, that I could not show because it would be too long, what you have is that you have a melt percolation front that changes the composition of the lithosphere. It crystallizes pyroxenes, so we call it refertilization because relative to the original Habsburgites, these rocks are easier to melt. They have lower melting points. This melting point, this melt percolation front can be followed by a melting front. That's what we see in Ronda. In lerts, we don't see it. It's also followed by a deformation front. So what you have is that we can move a lithosphere-asthenosphere boundary by making melts percolate the lithosphere, refertilize them, and then you can melt and redeform it. Do you see any evidence of such melt percolation fronts in the geophysical data? There's not a lot. I found some. First here, so we are in the western branch of the East African Rift. What they have mapped here, the Lindenberg and Wumpker, they have mapped an anomalous deep earthquake swarm that they have interpreted as tracers of magma motion in the lithospheric mantle at depths of 60 to 65 kilometers. For the same region, they have another set of data that indicates that they may have melts in the mantle lithosphere. So this is the receiver function. We have already seen this figure. So this figure here goes on the top of this one. So we have this lithosphere-asthenosphere boundary in this region. And here we have a mid-lithospheric reflector. And at depths between 45 and 100 kilometers, getting deeper towards the craton. And this reflector is associated with a very strong velocity reduction that was interpreted by the authors as the presence of melts in the lithospheric mantle. So maybe it's possible. Maybe we are seeing that kind of process in areas where the rifts are very, very young, so when you are starting to thin the mantle lithosphere. So we try to look also in some models to see if such processes may help bottom-up thinning of the mantle lithosphere. So we build up on old models that I'm showing here, where we are trying to look at the plume-lithosphere interaction and trying to see if the small-scale convection that is stronger in the plume wake because you have higher temperatures and lower viscosities can be enhanced. In these models, we could have some thinning, upwelling of the 1200 isotherm by 10 to 30 kilometers, not more. So here is the plume impact point, and the black lines are the isotherms once at the end of the models. These are the initial ones. You see that the 1200 is upwelled by 20 kilometers in this model. So we continued looking at this during the PhD of Roberto Agrusta, and he did a much more detailed study on the dynamics of this small-scale convection, trying to get scaling laws. And he could scale the minimum depth of to a 1300 isotherm, so the uplift of the lithosphere-asthenosphere boundary as a function of the local Rayleigh number on this layer. And you can see that the upwelling is very, very, very weak for cold plumes, the blue ones here. And as you get hotter and more buoyant plumes, you can get up to 30 kilometer thinning because of the small scale convection in the plume wake. The question, in 3D, you have the same kind of results, maximum 30 kilometers of uplift for very strong plumes. The idea is that maybe the presence of melt can also enhance the small-scale convection and get a stronger erosion of the lithosphere basis. And mainly based on 2 points, is that the presence of melt will reduce the viscosity. This is experimental results from Kolstad group that show that if you enhance the melt fraction, that's marked here, you can get a strong reduction in viscosity in the dislocation creep, that is grain size independent here. We also have a reduction that's not as strong in the diffusion creep, that is this part here, the white part of the table here. So what Roberto tried to test is if partial melting can get a stronger small-scale convection and a more effective erosion of the lithosphere. First, he tried very simple models of the variation of viscosity with the melt fraction, and a very simple anhydrous melting model, not take into account the depletion on the melting. And so here a linear variation of viscosity, here a step-like variation of the viscosity. And if you compare with a model with no melt, this is the uplift of the 1200 isotherm. You see that we enhance the uplift of the 1200 isotherm by 5 to 10 kilometers when you put melt in the system. Yet these models have up to 40% melt, so quite a lot of melt. It's quite unrealistic. And this is mainly because we are not taking into account that once a mantle fraction has molten, it will get harder and harder to melt because it gets more and more refractory. So what we try to put in the model is a critical fraction for both melt extraction and to the variation of the rheology with the melt fraction. So use the data from Takei and Holtzman that shows that even at very low melt fractions, 0.1%, you can have already quite a 1 order of magnitude decrease in the viscosity. And when you put this kind of data, you can have a very strong variation on what is the instantaneous melt fraction that you keep in the system. It's always, at least the threshold melt here is 1%, so everything that's more than 1% is artificially extracted from the system. But you also have the depletion. The depletion is dependent on the cumulative melt fraction. I'm finished. So the more you melt, the more you deplete. So the variation of the density will depend on something that accumulates with time, while the change in the viscosity that you implement in the model will depend only on the instantaneous melt fraction. So we have two different effects. And this is just to compare these two effects. This is one model, Plume model, where you have no melt. Here you have only the effect on the density, the fact that when you melt, the residue is more buoyant. So we have the density contrast here that is stronger. And you see that the small-scale convection starts earlier and is more active. Here you only have an effect on the viscosity. You see that since the instantaneous melt fractions are low, the effect on the viscosity is weaker than the one in the density. And here's the model we have both effects together. You see that relative to this one, you have earlier onset of small-scale convection and a stronger uplift of the 1300 isotherm. So this is just for comparing. The colored ones are models with different melt extractions. So from red to green, you keep more melt in the system. And you see that for strong plumes with a strong temperature difference, it does not make a big difference. For weak plumes, if you keep more melt in the system, you erode more the lithosphere. So it changes a little bit. And I get to the conclusions. What we have seen here is that the observations in natural systems constrain that you can have melt, percolation, and refertilization reactions that can allow the lithosphere-asthenosphere to move. And the Ronda data that I have not shown constrain that this kind of refertilization front can be up to 1 kilometer ahead of the melting one. And this is something that is dynamic, so you can get it propagating through the lithosphere. In all cases, you have the melt migration that will precede the deformation, so it will weaken, and it also refertilizes the base of the lithosphere, so it allows it to remelt. And you have strong interactions between the melt transport and deformation. You have strain localization, and you have layering of the melt, which will give a strong anisotropy of physical properties. And this is one of cartoons, Ben Holtzman's cartoons. The idea of this kind of process interactions can really have a strong effect on the formation of this very strong upwelling of the LAB in a narrow zone beneath the East African rift. The models show that if you couple deformation and melting, you can bottom-up thin the lithosphere in a very effective way. And some geophysical data point for melt in the mantle lithosphere up to shallow depths, but it's very weak, very few data up to now. And you have weak constraints when you use the geophysical data in the distribution and composition of these melts. However, all these observations are for very shallow lithosphere-asthenosphere boundaries. They are the only ones you can really look and have been exhumed. And in this very shallow lithosphere-asthenosphere boundaries, partial melting is very easy. The question is, maybe you can use this kind of observation that explain quite well the seismic data to extrapolate when you are seeing the lithosphere-asthenosphere boundary at much deeper depths where you are very far from the solidus, when it's not very easy to understand, to think that you can have lots of melting. And there are lots of other open questions in this kind of subject. The first one is that you have differences between the methodology and experiments and the natural systems. If you are working on mechanical anisotropy, this 30-degree angle can make a very, very strong difference. Maybe the explanation is that what we see in the nature is not the real melt topology. Maybe not. Maybe what we see in the crust shows that maybe you see the real one in melt systems. We still don't know very well the melt migration process. This kind of refertilization we see in lerts indicates you have very, very effective porous flow without cooling the melts very easily. But when you do the calculations, it's not very easy to get this kind of porous flow working for a very long time with very low melt fractions. You cool the melt quite easily. So it hints that maybe you don't know very well the thermodynamics of these biphasic systems. So, and that's all. Thanks.